So as I explained in the introduction, Febit has a unique ability for 3D printing at nanoscale resolutions. And this is something that is the main focus of f3ast. But before f3ast, there was a lot of development in this realm. And I would like to particularly highlight the works by Jason Folks and Harald Planck, and as well as Michael Uth and his group, where they developed these two softwares that have similar capabilities, and where, as you can see, they were capable of fabricating really complex 3D nanostructures, but in all cases with nanowires interconnected at given vertices. For this, Jason Folks, for instance, developed a very powerful simulation toolkit combining the Febit continuum model with Monte Carlo simulations, where he could predict what type of geometries could be fabricated and compare them with experiments. How did this work? So this way of operating is really powerful because you are simulating the full Febit process, and then you can compare with experiments and guide the 3D printing. So in experiments, what you do is you grow vertical pillars followed by segments, and these segments have given angles with respect to the vertical direction, which depend on the dwell time, for how long the beam has been scanned at each point, and then it moves to the neighboring point with a given overlap, typically between 1 and 3 nanometers. So by plugging in the simulation all the parameters necessary to describe a Febit process, it is then possible to compare the experimental work and the simulations looking at the segment angle. So you can see that when you get a good agreement in between experiments and simulations, that means that you are describing properly the Febit process, and therefore that can guide more complex geometries afterwards. However, this way of operating, because the complexity that I explained previously for Febit, restricts the type of geometries only to nanowire based ones. So no surface or volumes are possible. And there's another important point, that the simulations rely on tens of parameters. You can see here, for instance, all the parameters that are required in the simulations in order to describe the Febit process. Of course, many of these are very difficult to obtain experimentally, and many of them are obtained at ultra high vacuum, where the conditions are different than the standard Febit process that are done with Febit. So this is a really powerful way to operate, but of course it is limited to the type of geometries that we want to develop, and also is slower because you need to be simulating very complex geometries first that can take quite a long time before being able to 3D print. With f3ast, we have followed a different approach, and what we want to do as a goal is to use the same method as a standard 3D printer extruder. So we want to grow layer by layer complex geometries, and thanks to Febit, we will be able to do this with nanoscale resolution. So f3ast is the first Febit code able to print arbitrary 3D geometries. It's important to highlight that it's not based on simulations, but it's based instead on the Febit continuum model under specific conditions that I will explain later. And the key point here is that what we have also developed is a simple two-step calibration procedure that fits into the f3ast model, and that allows us to print directly. We don't need to do complex additional simulations. It is, of course, has its limits, but in a very nice and effective way, we can describe the Febit process, and therefore that allows us to fabricate complex 3D geometries. So this is the f3ast 3D printing algorithm in a nutshell. We will create a 3D object by any standard CAD software, the one that you prefer. This design will be plugged into the f3ast software using typically an STL file, which is the same as any 3D printer would use. In this case, it's this double curved structure. Our software will slice it, creating different layers. And for each layer, we will be computing what is the number of milliseconds that the beam needs to be on each spot in order to grow each layer. This is what it is shown here, where the software is calculating the dwell times, the time the beam needs to be on each spot, and for this we will be using the Febit model that I will show you later. The software can also take into account additional effects like beam heating, defocusing, and gas flux anisotropy, which could be an intermediate step before calculating the times necessary for 3D printing. Once these times have been calculated, we can plug them as typically string files into the pattern generator of one of these SCM systems, giving us a result, the fabrication, and you can see here an SCM image of a 3D object with very nice agreement with the design that we initially targeted. So in order to perform the modeling, of course, we will perform the modeling, but we will need from the experiments some type of calibration. And this is one of the important points of FIST as well, that we have developed a simple two-step calibration. In the first one, we calculate growth rates, and in the second, we calculate interaction volumes that are fed into the model, and this allows us to basically calculate the correct dwell times for 3D printing. In order to take into account additional effects, if necessary, they are not always important, but if necessary, we may need to do additional calibration that take into account this, and it brings some second order corrections to the model.